Hi everyone, welcome back to Causality with Boris, broadcast from Sobolev Spaces. In this video, I'll share some thoughts on inverse probability weighting. Three main topics in today's lesson: weighting conditional risks, pseudopopulations, and the role of stratification variables. Make sure you watch chapter 4. There will be a quiz at the end. As always, there is extra material attached to this video. Click the link in the description and you will receive it. Treatment effect is the difference between the average of potential outcomes in all treated and all untreated units. These are the same units under two conditions. And this is our starting point. When outcome takes only two values, treatment effect is the difference between the marginal risks, and they are the averages of conditional risks. Let's see it on the board. Suppose these 10 observations is the entire study population. There are two alternative treatments, and the outcome is binary. For simplicity, we code it as 0 or 1. The observations are grouped in two strata, S0 and S1. And this table is a reminder that outcomes of alternative treatments are not available in the same units. So we cannot calculate individual effects and average them. Nor can we use the difference between crude risks in treated and untreated. Our concern is that strata and treatment effects could be mixed. Instead, we find marginal risks as the averages of within stratum risks weighted by strata prevalence. To make this simple, strata prevalence is 50%. Therefore, the marginal risk, if all were treated, is the sum of conditional risk in strata multiplied by half, which is 0.42. Similarly, if all were untreated, the risk is the sum of stratum-specific conditional risks times 1/2, which is 0.58. This is stratification and averaging by strata prevalence. Alternatively, we can weight observations by the inverse of their probability of being in the treatment group in their stratum. To illustrate this, let's go back to the table with these 10 hypothetical observations. First step is the inverse probability weighting in the treated group. In stratum S0, the treatment probability is 2 in 5. The inverse probability weight is 5/2. In stratum S1, the treatment probability is 3 in 5, and the weight is 5/3. Marginal risk in the treated group is the sum of weighted outcomes, which is 0.42. Next, the inverse probability weighting in the untreated group. For observations with no treatment, the probability of being sampled in control group is 3 in 5 for stratum S0 and 2 in 5 for stratum S1. The weights are 5/3 and 5/2. Marginal risk in the untreated group is the sum of weighted outcomes, which is 0.58. Applying inverse probability of treatment creates comparable samples of treatment groups. All groups have the same distribution of stratification variables as the overall study population. Often such weighted samples are called pseudopopulations. Let's take a closer look at this. Suppose a treated unit has a 0.2 probability for being sampled in a particular stratum. It means for every treated unit, there is another 4 units in the control group of the same stratum. If we want to find out what would happen if everyone had been treated, we need to check the potential outcomes for these control units. We say potential because we look at them as if they had received treatment. How many of them would have outcome 1 and how many of them would have outcome 0? The best way to answer these questions is to find the post-intervention probabilities for treatment, outcome, and strata, and then link them to probabilities we can find from data. In his 2009 book, J.J. Pearl proves that the post-intervention joint probability is equal to the product of two pre-intervention quantities. One describes how often the outcome occurs depending on treatment and strata, and the other describes how often the treatment alternatives are chosen in non-experimental setting. At this point, we have two options: weight conditional risks by strata prevalence, or weight the joint probabilities by the inverse probability of treatment in a given stratum. And they produce the same result. I should note that the inverse probability weighting works for aggregate data too. These are the counts of observations. Suppose there are nz units in stratum Z. The number of treated units with a particular outcome is proportional to the joint probability for treatment, outcome, and strata. Pearl's formula in fact tells us that this number would increase by the inverse probability factor if everyone had been treated in that stratum. Let's go back to that unit with treatment probability of 0.2. We expect that every unit in our sample represents 5 units in the study population in which all are treated, all with identical treatment outcome pattern. This last observation sheds light on the mystery of pseudopopulations. So many mysterious terms in the causal analysis, right? Potential outcomes, counterfactual treatments, pseudopopulations. You see, the core concept here is a change in the proportion of observations by the treatment probability. We find the joint probability for treatment, outcome, and stratum. Then we weight it by the inverse probability of being in a treatment group within each stratum. Again, it produces identical strata distributions in treatment groups after the observations are weighted by the inverse probability of being sampled with their actual treatment within their respective strata. We apply these inverse probabilities to the number of observations and to the number of outcomes. It produces the same number of observations in treatment groups within each stratum. The weighted observations inflate the number of outcomes in the treatment groups that are underrepresented in each stratum. Pearl's formula, in fact, tells us this number would increase by the inverse probability factor if everyone had been treated in that strata. Let's recap. Applying inverse probability weighting creates hypothetical populations all equal in size, and they all have the identical strata distribution. Each hypothetical population represents the study population, but with different treatments. And each stratum has an equal chance to be sampled in the treatment group. We achieve our goal of comparing like with like. Just one more thing. You may hear that inverse treatment probabilities reduce selection bias in observational studies. Well, the question whether the weighting reduces a bias should be addressed by the selection of variables, or broadly by the assumptions in the dependency graph, and not by the estimation technique. You see, regardless of the variable choice, stratification places units into mutually exclusive strata. Treatment effects are then estimated in each stratum and averaged over strata. That's how we find the overall effect. One limitation of stratification is that dividing units in different strata may not be meaningful. As a result, variation in stratum-specific effects may have limited interpretation. We often hear that inverse probability weighting is free of this limitation, supposedly because any set of variables can be used. Let's return to Pearl's formula. It says, if strata variables satisfy the backdoor criterion, then the difference between the marginal risk is caused by being in treatment group. And then effect size is the average of stratum effects weighted by the strata prevalence in the study population. Now, this is important. When we move from conditional risk to inverse treatment probability, we retain stratification. In fact, we are still averaging over strata. And here is another thought. The inverse probability weighting is valid only if the stratification variables that determine the weights satisfy the backdoor criterion. Otherwise, the method may introduce more error than a regression adjustment. Ideally, we'd use all direct causes of treatment for stratification variables. In practice, however, this may be too many to fill all strata with observations. The backdoor criterion points to a minimal set using assumptions in the dependency graph. Again, for interpretation we may prefer a subset of direct causes, but this criterion says nothing about stratification variables being predictors of treatment. When stratifying by variables from the criterion, we use sample proportions of treated units in strata without expecting the strata will be good classifiers. Now, you give it a try. What's the ending of this sentence? The purpose of inverse probability weighting is option A, to have comparable samples of treated and untreated units, or option B, to match treated and untreated units on some factors. Pause the video and pick the ending. Did you pick option A? Awesome. So here's the main message of this video. The inverse probability weighting creates hypothetical samples. They are all equal in size and have the same strata distributions. We call them pseudopopulations. You've learned that inverse probability weighting is only applicable if stratification variables satisfy the backdoor criterion. Otherwise, it can introduce bias. Don't miss the key idea that once treatment probability is applied, each stratum has an equal chance of being sampled in the treatment group. Keep on watching.